All right, let's get started. Before we start new material today, let's remind ourselves of what we talked about last time. So what did we go over last time? First we went over just logic. Well, that was the second thing we did, actually. First thing we did is we went over a few definitions. We talked about how in mathematics we have to know exactly what we're talking about. We can't make statements like the sky is blue, right? Bunch of nonsense. We need to be precise in what we're talking about. So we talked about the definitions of a few things. Do you remember what they were?
Prime, even, composite.
So we talked about an integer. So this is our symbol for integers. What does it mean to be an integer? It means you're in this set, -3, -2, -1, -0, 1, 2, 3, oops, dot, 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 whatever, and dot, dot, dot. Right? So to be an integer means that you're a member of that set. So now we know what it means to be an integer. What else did we talk about?
What it means to be even.
Even. Before we can do even, what did we need to find? We can say even really quick. What's even?
Even is an integer. There exists an integer that is divisible by 2.
Integer, yeah, even is an integer divisible by 2. But then we had the question of what's divisible.
Yeah.
So what does it mean to be divisible?
There exists a C such that B times C by B equals A.
Right, so we say A divides B. That's logically equivalent to. There exists some integer C. There exists C in the integers such that what?
Such that B times C equals A.
Other way around. A times C equals B. A divides B. A is a factor of B.
Yep.
Oh, yeah, because last time you did B divides A.
So if I do 8 divides 2, that equals 4, right?
Nope.
No, that equals false. This has nothing to do with division. Division is an operation. This is a statement that is either true or false. Does 8 divide 2? Is 8 a factor of 2? No. Alright? Nothing to do with divide by. Don't let the fact that they have similar words throw you off. Have that problem every year. Okay, so we talked about divisible, we talked about even. What else did we talk about?
Odd.
Odd. What does it mean for an integer to be odd?
X equals
2x
2x
plus 1.
minus 1.
Yeah. X is odd if I can, or what should we call the integer? A and Z is odd if and only if there exists some other integer x in Z such that A is equal to 2x plus 1. If I can express some integer as 2x plus 1, it's odd. Right?
Yeah.
And essentially the even definition, a logically equivalent version of an even definition is if I can express it as A equals 2x, it's even. If I can express A as 2x, that means it's divisible by 2. It's 2 times some integer. So all even integers can be expressed this way. All odd integers can be expressed this way. If A is even, we can express it like that. If A is odd, we can express it like that. Right?
Mm-hmm.
That make sense? What other definition do we talk about?
Prime.
Prime. What's a prime number?
It's where the only divisible factors is 1 in itself.
It's only positive
Positive.
divisors are 1 in itself. And what was the other condition for it to be prime?
Had to be positive.
Had to be greater than 1. So P is prime if it's greater than 1, and its only positive divisors are 1 in itself. Right? Does that make sense? And then finally we had composite. What does it mean to be composite?
We thought you could have.
Yeah, this one we might need to write out as well.
It's not prime.
Not prime? No, that is not the definition of composite. Is 1 prime?
No.
No, so it's composite.
Right.
No. What about -7? Is that prime? No, why not?
Because it's less than 1.
Yeah, prime numbers have to be greater than 1. Maybe we should just put prime up here again, just to make sure we all understand. Prime. That means P is prime if it's greater than 1 and its only positive divisors are 1 and p. That's what it means to be prime. So now composite, what does it mean to be composite? So we'll call the number c for composite. How do I know when c is composite? C has to be greater than 1, right? And there must exist some integer a. So there must exist a in the integers. Must exist some integer a such that a divides c and 1 is less than a is less than the number we're talking about, c. Give me an example of a composite number. 4. How do you know 4 is a composite? First off, it's greater than 1. Does there exist some integer that divides 4 and is in between 1 and 4?
Yes.
Yes, 2. Right? Does 2 divide 4? Is 2 a factor of 4?
Yeah.
Yeah. And 2 is between 1 and 4. Therefore, 4 is composite. Is 5 composite?
No.
Now, 5 is greater than 1, it works for that. Does there exist some integer that divides 5 and is in between 1 and 5? No. The only positive integers that divide 5 are 1 and 5. So 5 is prime. Okay, so those were our major definitions, and those were all the definitions we covered. And then outside that, we just covered logic, right? Okay, so today, we're going to focus on proof. Chapter 5, or section 5, I mean, is direct proof. So we'll learn how to do a direct proof. Section 6 is proof by counterexample. And then section 7 will be Boolean Algebra, which is basically just logic. That's why I give you a lot of logic when we first cover it, because it's basically the same thing as Boolean Algebra. So we'll do each of those. Okay, so now we're jumping into proof. First off, what is a proof?
An explanation.
An explanation.
Statement that proves something.
A statement that proves something. Rule number 1 with the definition, you can't use the word you're trying to prove in its definition. So you can't define proof using proof.
It's a written out explanation for why something is either true or false.
Yeah, in short, it's an implication, alpha implies beta, that we show is always true. Every single theorem, every single proof can always be stated as an if-then statement. Sometimes it might not be as obvious how to state it as an if-then statement, but every proof can be stated as an if-then statement.
Okay.
So, a proof is showing that some if-then statement is true. That's all it is. And hopefully in your homework I made you write out a bunch of statements as if-then statements. The whole point of that exercise is when you see something you're supposed to prove, your first step is to really think about it in terms of an if-then statement. All right. So, when we prove something, we show it's an implication that's always true. It's impossible for it to be false. We cannot prove something with just a bunch of examples. We talked about this last time. Does infinite examples prove something if I can show it's true infinitely many times? No. We have to show that it's always true. That's different than showing it's true with infinite examples. Give you an example of a statement like that. All primes are odd. I can prove that. 3, 5, 7, 11. How many you want? 13, 17. Tell me how many primes to write. I can continue writing primes forever. And they'll all be odd. So are all primes odd? No. What am I forgetting? 2. There's only one prime that's even, and there's infinitely many that are odd. When you're trying to prove something and you think, well, I came up with a bunch of examples where it works, therefore it must always work, you could be forgetting the one and only one example where your theory doesn't work. You could have some idea of math and you try it out a billion times and it seems to always work. Maybe it works infinitely many times and there's only one case where it doesn't work. How hard is it to find one in infinity? In this case it was trivial. In other cases you can imagine how it could be hard. So no, infinite examples is not enough. Now statements that we think are true but we don't have a proof for, we call a conjecture. And so one of the most famous conjectures out there is the Goldbach conjecture. The Goldbach conjecture says that every even integer greater than 2 is the sum of 2 primes. So let's look at all the even integers greater than 2. 4, is that the sum of 2 primes? Yes. 6, is that the sum of 2 primes? Yes. 8, is that the sum of 2 primes? Yes. 30, is that the sum of 2 primes? Yes. We have computers cranking away at this, trying higher and higher and higher and higher sums. And it seems to always be true. We haven't found one case where it doesn't work yet. But that's not a proof. And you become very famous if you can figure out how to prove that thing. So, things that seem to always work, we call conjectures. Things that are proven to work, we call theorems. Okay, so today we're going to be focused on how to do a direct proof. Now, unfortunately, there is no rules for this is how you prove something. And oftentimes, the problem that you're solving requires some sort of trick, some sort of insight that you just have to glean somehow. Like that problem I initially gave you guys. When we had a minus x times b minus x times c minus x, all the way to z minus x. Now that seems like a super complicated problem. Until you realize, what was the trick?
X minus x.
Yeah, one of those terms is going to be x minus x. What's x minus x?
0.
0. What's 0 times anything?
0.
0. So this whole thing evaluates to 0. And you had to just get some insight to solve that problem. And there's no training that you could have really had prior to now to teach you how to solve that problem. You already knew x minus x was 0 before you did that problem. And you already knew that 0 times anything was 0. You already had all the information you needed to solve that problem, and yet you got stuck on it. That's often how it is with proving something. You have everything you need to know, and you just need to have that insight. So we're going to try and make this as much a procedure as we can for your first few proofs to get you used to proving things, but there's eventually going to come a point where it's all on you. So, as a general rule, how do we prove things? First, we restate whatever you're trying to prove as an if-then statement. Next, we assume the antecedent. What's the antecedent of an if-then statement? If I say alpha implies beta, what's the antecedent? Alpha. So we assume alpha is true, and we write the conclusion as our last step. Then we do something called unraveling definitions. After that, it's all on you. So let's do an example of this so you can see it in action. So we're going to prove proposition 5.2. Propositions, theorems, same thing. All right. The proposition is the sum of 2 evens is even. That's what we're trying to prove. Now we need to write that as an if-then statement.
Okay.
So how can we write this as an if-then statement?
If x is the sum of 2 evens, then x is even. Is that right?
If x is the sum of 2 evens, then x is even. That could work.
If the sum is of 2 evens, it is even.
If
then it
x,
is even.
y, and z are even, comma, then x plus y is even. Probably the most useful way to rewrite that.
Okay.
This says the sum of 2 evens is even. This says if x and y are even, then their sum is even.
Yeah.
Right? Everyone understand how we just restated it as an if-then statement?
Yeah.
That's all we've done so far. Okay, so step 1. We assume the antecedent. We basically say let, and then we write out the first part of the if. Let x and y be integers such that x and y are even. So that's our starting point. And we ultimately need to show, conclusion, last step, therefore, x plus y is even. State our conclusion, and we'll be done once we get to that line. So here's our starting point, here's our ending point. We got to fill in everything in between. right? So we just really did, we stated it as an if-then statement, we assumed our antecedent, and we wrote out our conclusion. That was step 2. Now step 3 is unravel definitions, which means just use your definitions to rewrite information about these things.
Okay.
So I know that x and y here are even. So that's information I have, and I can use that information.
Okay.
Right? So 2. Since x is even, what do I know?
That you can pull 2 out of it.
That 2 times some integer equals x. Since x is even, then there exists some integer, we'll call it a in z, such that x is equal to 2a. That's what it means for x to be even. It's 2 times some integer. What else do we know?
Same thing about y.
We know y is even. Alright? 3. Since y is even, comma, there exists some integer, we'll call it b in z, such that y is equal to 2b. Right? Okay, so now we've unraveled our definitions at the top. We have a definition at the bottom, therefore x plus y is even. We can now unravel this definition upwards. What does it mean for x plus y to be even?
Then it's also divisible by 2.
Yeah, so above it we could say, then there exists some integer c, we'll call it, in z, such that 2 times c is equal to x, we'll write the x plus y first. X plus y is equal to 2 times c. Right? If I could say that x plus y is equal to 2 times c, x plus y is even. Right?
Okay.
If I knew this line, I know this line.
Do we get to assume stuff like other operations and order of operations and all that kind of stuff? Do we have to define that?
We get to assume numbers and arithmetic.
Okay.
That's what you get to assume. Numbers and arithmetic. Okay. So now we're stuck. We've unraveled this definition, what it means to be even. We've unraveled the definition up here, what it meant for those two to be even. Now we're stuck. Now we somehow need to connect this statement with this statement.
You just make.
And this is where it's all on you.
Okay.
There's no tip, there's no trick. You just got to see how this statement is connected to the statements up here. Now what do we have in this statement right here that we have up here? X and y. Notice that this statement is saying something about x plus y. Right? So a very natural thing here would be to then look at what x plus y is. So then, x plus y is equal to what?
2b plus 2a.
2a plus 2b. You see that? Now what can I do to this?
Factor out of 2.
Factor out of 2. So this is equal to 2 times a plus b. 5. Let c equal a plus b. We're just going to relabel a plus b the number c. That's perfectly fine. Just relabeling. 6. Then there exists some integer c such that x plus y equals 2c. Because c is equal to a plus b. And x plus y is equal to 2 times a plus b. 7. And there we go. We're done with our proof.
Okay, so what I would have done is I would put the 5 before I did the 4, so the let c equals a plus b. Would that be bad?
Doesn't matter. C is just a relabeling of those things. I would have been fine if you cut out c altogether and went from 4 to 7.
Okay.
Because this is 2 times an integer plus an integer, that's just an integer, 2 times an integer. So x plus y is 2 times some integer.
Okay.
But it's good to plug in everything precisely at first and get a good feel for using these definitions. Alright, is there any weird steps in this? Does all of this make sense? Let's go over it one more time. We're trying to show that if x and y are even, x plus y is even. So I'll let x and y be even integers. Since x is even, we can write it as 2 times some integer. And since y is even, we can write it as 2 times some integer. Call those integers a and b. Now we want to look at x plus y and show it's even. So x plus y then is equal to 2 times some integer plus 2 times some integer, which is equal to 2 times some integer. So x plus y is 2 times some integer. Call that integer c. So then there exists some integer c such that x plus y is equal to 2 times c. Therefore x plus y is even. Good? Alright. Let's do another one. Let a, b, c be integers. If a divides b and b divides c, then a divides c. That's what we need to prove. Alright, same steps as before. If you have the let here and it's throwing you off, you can always put the let as part of the if. And I'll show you that here. If a, b, c are integers such that a divides b and b divides c, comma, then a divides c. You see how that's what we're trying to prove? So, if they put a let before the if, it's still part of the antecedent. And so it's still just an implication that you're proving. Make sense? Okay, so what is the first line of my proof going to be?
Let a, b, c be integers.
Let a, b, and c be integers such that a divides b and b divides c. Okay, there's our first step. Now what should we do?
Right. You just write out what it means to be divisible.
Well, now we're going to go to the bottom and write out our conclusion.
You had to.
I know it's kind of awkward for those of you who are already used to proofs to do the top, do the bottom, fill in between. You want to just work from the top down. You'll get to that point. So this is kind of a tedious way of proving. It's a great place to start from. Okay, so our very last line we know is going to be what?
A is divisible by c.
Therefore, always therefore a divides c. And we're done. This is why you don't get any credit in this class for writing the right answer, right? You don't just get to write that and be done. Okay, so now what do? So we stated it as an if then, we assumed the antecedent, and we wrote the conclusion. Now what should we do?
Unravel our definition.
Unravel our definitions. 2. Since a divides b, comma, what does that mean?
There's some integer x.
There exists some integer x such that
a times x is b.
perfect. So since a divides b, what does that mean? It means a times some integer equals b.
Yeah.
Does 4 divide 8?
Yeah.
Yes, because 4 times 2 equals 8. Does 50 divide 100? Yes, because 50 times 2 equals 100. So if a divides b, then that means there exists some integer, we'll call it x, since Jeremy chose x. There exists some integer, x, such that a times x equals b. Okay, that unraveled that definition. Now what?
We could do the same with BC.
Perfect. 3. Since b divides c, comma, then there exists some integer, which we call it y, such that there exists some integer y, such that b times y equals c, right? Okay, do we have any more definitions to unravel there?
No.
No? What about at the bottom? Do we have a definition to unravel here?
Yes.
Yes. What does it mean for a to divide c?
There's z in the integers.
Then there exists some integer z such that a times z is equal to c, right?
Yeah.
There we go. Now, the hard part. The part that's 100% on you. There's no trick, procedure, anything like that. You just have to connect these two.
Substitute
Substitute.
the AX for the B in
Perfect.
23.
So he's saying that these two are connected. Let's connect these two pieces of information. This is connecting A to B. This is connecting B to C. If we combine these two equations and we connect A to C, and notice that this is talking about connection of A to C. So that's exactly what we want to do. 4. Then C is equal to B times Y is equal to, we're going to substitute out the B part.
A times X times Y.
A times X times Y. Everyone see how we got that?
Yep.
B is equal to A times X. So B is the same thing as A times X. Right? Okay, now what?
We can define what Z is.
What should Z be?
X times Y.
Let Z equal X times Y. And we're done. And you can pretty much say it, we're done here. C is equal to A times some integer. X is an integer. Y is an integer. An integer times an integer is still just an integer. So we have C is equal to A times some integer. We call that the Z. So then we got C is equal to A times Z. So this was line 6 and this was line 7. Everyone follow that? Cool. Next. If x is an integer greater than 1, then x cubed plus 1 is composite. Oh geez. How on earth are we going to prove that? So if x in z, if x is an integer such that x is greater than 1, comma, then x cubed plus 1 is composite. So it's guaranteed to not be prime. How on earth are we going to prove that thing?
Well, let's start with writing our.
Yeah. Can seem overwhelming at first. Let's start by just following the steps. What's our first line going to be? What am I writing? Let
X in Z such that X is greater than 1.
It's almost like you were reading the answer somewhere. You were able to replace an if with a let. Should be good. All right. What's our conclusion going to be? Tell me what to write. Therefore,
X cubed plus 1 is composite.
x cubed plus 1 is composite. All right. Now we got to somehow connect these things. Definitions. Here we're kind of stuck. X is an integer where x is greater than 1. We don't have any definition to unravel there.
Well, we could talk about composite definition.
We can talk about the definition of composite. So, then there exists some integer, we'll call it y in z, such that y divides x cubed plus 1, and 1 is less than x cubed plus 1 is less than, 1 is less than y is less than x cubed plus 1. Right? Now we gotta find this y thing. We gotta find some y thing that's always between 1 and x cubed plus 1 that divides x cubed plus 1. Now, what is something that divides x cubed plus 1? We need a factor of x cubed plus 1. This is begging for us to factor it. What goes into x cubed plus 1?
X.
X doesn't go into that.
Okay.
You don't know how to factor polynomials?
I don't know. I do.
So we need a way of rewriting x cubed plus 1 as some factors.
Okay.
What goes into it? X minus 1. You guys ever learned syntactic division?
Yes. A while ago. Yeah.
A while ago?
Mm-hmm.
Alright, well, here's the answer. X squared minus x minus 1.
Why are we using minus?
Distribute it through and see what you get. So distribute the x through to all of those, and what do you get? X times x is?
X cubed.
X cubed. X times negative x is?
Negative x squared.
Negative x squared.
Wait, x
Oh.
times x is squared. Oh wait, x times x squared.
Am I doing this wrong?
The x has to be negative, isn't it? Or that.
Is that right?
Yeah.
X cubed minus x squared minus x, put the 1 through, we get x squared minus x minus 1.
Oh, that.
I'm still doing something obviously wrong. Oh, this is gonna drive me nuts. We are missing something stupid simple. X plus 1 I think that's a minus. Oh, and then everything's positive. Okay. Sorry, that was terrible. Okay, redistribute through. X cubed plus x squared plus x is distributing the x through.
Okay.
Now distribute the negative 1 through. You get negative x squared minus x minus 1.
That's the same place you were.
No, no, it's not.
Oh, sugar. That is still wrong. That's for x cubed minus 1. Now I wonder if I wrote the problem right. Should look at this stuff the night before rather than just throwing it up. Because we are missing something stupid, obvious. It's terrible that no one is seeing it.
Oh, dude, imagine
Donnie, do you think you're as smart as Sheldon Cooper?
Now. Not as far as he's supposed to be. Oh my wow. Alternate the signs. And I should just do a general proof of this thing. Still make sure I'm not making any more stupid mistakes. Obviously it has to be plus 1, okay. So that's plus 1. Alternate the signs. Positive, negative, positive. Okay. Now let's make sure that we didn't screw anything up. Distribute the x through, what do we get? X cubed minus x squared plus x. Distribute the 1 through, what do we get? X squared minus x plus 1. Okay, there we go. Now, when you add them together,
It's x plus 1.
then you're going to be left with x cubed, those cancel out, plus 1. You see that?
Mm-hmm.
Now, we could have just done the synthetic division here. Remind you of synthetic division. So I am taking x cubed plus 1, and I'm dividing it by x plus 1. Maybe we should have just done this to begin with. X cubed plus 0x squared plus 0x plus 1 as placeholders. Same way you do long division, right? Think about that as like the hundreds place, the tens place, the ones place, or thousands, hundreds, tens, ones. Similar. And we're dividing this by x plus 1. How many times does x go into x cubed?
3.
X squared times. Because x squared times x is x cubed. Right? So x goes into x cubed, x squared times. Now we're going to take that, multiply it by this, and subtract. Same way you do long division. X squared times that gives us an x cubed plus 2x squared. Right? Now we're going to subtract this from this, so that becomes negative, that becomes negative. Put the line here, x cubed minus x, that's 0 minus 2x squared. Bring down your next term. Okay, how many times does x go into minus 2x squared?
Where did you get the 2 for x squared?
I don't know. Out of nowhere. Right out of my hat. Thank you. Good. Alright, so we did that right? X squared was x cubed, x squared was x squared, and then we subtracted it.
Oh, okay.
Okay, so that minus that is 0, that, well now we're adding. That plus that gives us this. Bring down our next placeholder. Okay, how many times does x go into negative x squared?
X.
Negative x. Negative x times x is negative x squared. Right? So now, same thing, what's negative x times x?
Negative x.
Negative x squared. What's negative x times 1? Minus x. Now we're going to subtract this from this, which makes that positive, that positive. So when you bring those together, obviously your outside term should always go to 0, and we have a plus x. Bring down our 1, plus 1. How many times does x plus 1 go into x plus 1?
1 time.
Exactly 1 time with no remainder. So this times this gets us back where we started. Okay, that's synthetic division.
Oh, we could just looked up there.
Well, yeah, that was trying to do it in my head, remembering rules. And I was mixing it up with, I know I was mixing it up because I was thinking about this as a difference of cubes, not as a sum of cubes. Difference of high order terms are always easy to do. Sums not. So something like if you wanted a to the 5 minus b to the 5, that's easy to factor. You pull out the a minus b, and then it's going to be a to the 4 plus a to the 3b plus a squared b squared plus dot dot dot, all the way to plus
Super simple.
b to the 4. It's long, but there's a brute force formula for doing those things. And so that's how I was initially thinking of that. Which is why I was getting so screwed up. Anyways, there we go. We factored this in. X cubed plus 1 is equal to that times that. Right? Now if I can show that one of these two things is always in between 1 and x cubed plus 1, then we're done. Remember what we're trying to show. We're trying to show that this number is composite. How do I show it's composite? I show it has some factor that's between 1 and itself that divides it.
So x plus 1.
X plus 1 looks like the easier of those two to deal with, right?
Yeah.
So let's deal with x plus 1. So what do I need to show about x plus 1? I need to show that x plus 1 is greater than 1, and I need to show x plus 1 is less than x cubed plus 1.
Okay.
Right? So, since x is greater than 1, comma, then x plus 1 is greater than 1 plus 1, which gives us that x plus 1 is definitely greater than 1. Since x is greater than 1, we can add 1 to both sides of the inequality, it doesn't change anything. Right?
Right.
Since x plus 1 is greater than 2, x plus 1 is definitely greater than 1. Good? 4. Something about multiplying numbers. If I take a number greater than 1 and I square it, does the number get bigger or smaller?
Bigger.
Right, if you take something like 2 and you square it, you get a bigger number like 4. On the other hand, if you take a number like 1/2 and you square it, what do you get? 1/4. It gets smaller. If you take a number that's exactly equal to 1 and you square it, what happens?
6.
It doesn't change. So if you square numbers smaller than 1, they get smaller. If you square numbers bigger than 1, they get bigger. If you square numbers exactly equal to 1, they stay 1. Make sense? So, since x is greater than 1, I know that x squared is greater than x.
Okay.
And I also know that x cubed is greater than x. Every time we multiply x by x, we just make it bigger. Which gives me that x cubed plus 1 is greater than x plus 1. Add 1 to both sides. 5. Let y equal x plus 1. Then there exists an integer y such that y divides x cubed plus 1, and y is in between 1 and x cubed plus 1. We showed that x plus 1 is less than x cubed plus 1, and we showed that x plus 1 is greater than 1. A bunch of different ways we could have shown those two things, but we did it. So now this is 6, and now this is 7, and we're done.
Do proofs always end in 7 lines?
No,
So not coincidence.
I don't know. It might have been coincidence today. I've been paying attention to that. Okay, let's do the next one. X is even if and only if x plus 1 is odd. Okay, how do we prove if and only if statements? Do you remember what if and only if was?
It's an implication error both ways.
It's an implication both ways. If I say alpha, I'll write down here. If I say alpha if and only if beta, then that means alpha implies beta and beta implies alpha. It's two implications. So if and only if proofs are two proofs wrapped together in one. So I need to show first alpha implies beta, and then I need to show beta implies alpha. So I need to show that if x is even, x plus 1 is odd, and then I need to show if x plus 1 is odd, x is even. And showing an implication one way does not guarantee the implication the other way. Give you an example of where it doesn't work. X equals 2 implies x squared equals 4. That doesn't necessarily mean that x squared equals 4 implies x equals 2. X could have been negative 2. So not all implications automatically go both ways. We need to prove that this one does go both ways. That x being even implies x plus 1 is odd, and x plus 1 being odd implies x is even. Okay?
Okay.
So proof. X in Z is odd if and only if x is even. If and only if x plus 1 is odd. Okay, so since this is two implications in one, when you're doing an if and only if proof, it's often the case that you'll see arrows to the side like this, saying which part of the implication we're proving first. So first I'm going to prove that if x is even, then x plus 1 is odd.
Does using if and only if count as a statement that's if then? Because how to prove starts with stay as if then.
It's two implications wrapped together in one. It's this implication and this implication.
So it still counts.
So you view it as two proofs now, basically, if you want to follow the same root procedure.
Yep.
So I need to prove two things. I need to show that if x is even, then x plus 1 is odd. When I'm done with that, I need to show if x plus 1 is odd, then x is even. So first I'm going to prove it this way. So what is my first line going to be?
Perfect.
Let x in z x be an integer.
Right. Let x and z be even. What are we trying to show? We're trying to show that x plus 1 is odd.
Yeah.
We're proving if x plus 1 is even, or we're proving that if x is even, then x plus 1 is odd. So let x be even, we need to now show that x plus 1 is odd. Alright, since x is even, what do we know about x?
That it's divisible by 2.
2. Then there exists some integer a such that x is equal to 2a. Okay, so then what does x plus 1 equal?
2a plus 1.
Then x plus 1 is equal to 2a plus 1. So now what do you know about x plus 1?
It's odd.
It's odd. It's 2 times an integer plus 1. That was the definition of odd.
Do we need to write out the definition of odd then?
This is the definition of odd. If it can be expressed as 2 times an integer plus 1, it's odd. That's its definition. So therefore, x plus 1 is odd. Right? Now we're going to go the other way. So then we put an arrow pointing the other way, showing that, now we're showing that this implies this. So what should I write?
Let x plus 1
Yeah.
be odd.
Now, comma, let x in z such that x plus 1 is odd. Right? Let x be an integer such that x plus 1 is odd. Okay, if x plus 1 is odd, what do we know about it?
2a plus 1.
Yeah, then there exists some integer, we'll pick a different integer, just so we're not repeating it there. Then there exists some integer b in z, such that x plus 1 is equal to 2b plus 1. That's what it means for x plus 1 to be odd.
Now cancel
Now
the
what?
ones.
7, perfect. Then x is equal to 2b. 8. Now what?
Therefore, x is
Therefore,
X is even.
x is even. Now I guess we technically skipped a small step, because with even, this isn't a definition of even. The definition of even is divisible by 2, so we could have said, therefore x is divisible by 2, therefore x is even. I'm fine with you making that leap. And now we're done. So we showed it both ways. So that's how you prove if and only if statements. It's 2 proofs wrapped in 1. Good? Alright. Let's try another one. We did proposition 5.5, now we're doing 5.6. If a, b, c, and d are integers, such that a divides b, b divides c, and c divides d, then a divides d. Okay.
So it's proposition 5.3 but with another.
Good. Yeah. You see, we've already proved something with proposition 5.3. The point of this exercise is don't reprove what you've already proven. Use what you've already proven to help you with your next proof. But let's write it out. So if a, b, c, and d are integers such that a divides b, b divides c, c and c divides d, and c divides d, comma, then a divides d, right? So what's my first line?
let a, b, c, d.
Perfect.
The integers.
Let a, b, c, d be integers such that a divides b, b divides c, comma,
Let's see.
and c divides d. Okay, now what?
Conclusion.
Yeah, we can go around our conclusion, but we'll assume that we can just keep working with it. If we get stuck, we'll go to the bottom and write our conclusion and try working backwards, if it helps. All right, so I know that a divides b, and I know that b divides c. So what do I know from that?
A divides C because of
A divides c, 2. Then a divides c by proposition
5.3.
5.3. So now, I know A divides B, A divides C. Oh wait, sorry. Now I know A divides C and C divides D.
Yeah.
Maybe I should put since here. Let me say it that way. I think you'll see it there. Since A divides B and B divides C, comma, then A divides C. And that's prop 5.3.
Can't you just
Are you missing any students?
Nope.
can't you just say in the next line that because of prop 5.3 then, and because like what you just did there, then
Yeah, you can prove
A
it the same
divides
way,
D.
can't you?
Right, so
You
since,
still have to do it 'cause
now I have since A divides C and
C divides D.
C divides D, perfect, comma, then what?
And A divides D.
Then A divides D. And this is once again by prop 5.3. 4. Therefore, A divides D, and we're done. Or you could have put the square there if you wanted, if you don't want to end it always in a therefore. But always nice to end it in therefore. Makes it clear to the person reading it that you're done.
But that's what the square is for.
And a little box.
Well, when you say therefore, then it means that the thing you're about to write, it's a reminder that that's exactly what you were trying to prove. They might have lost track here that this is what you're trying to prove. So, write for your audience, as a general rule of thumb, write so that the person next to you could read your proof and understand every step you took. You're not writing for me, you're not writing for a math expert, you're not writing for a toddler. You're writing for the person next to you. So if you don't think Hayden needs the explanation, you don't need to put it in there. If you think you'd lose Hayden, put it in there. Okay. We did all those, right?
Yeah.
Okay. And then one over here that I forgot to write, and so I wrote it in the wrong spot. One more proof of ours. This time we're going to prove if x is greater than 2, then x squared is greater than x plus 1. If x is greater than 2, comma, then x squared is greater than x plus 1. Now it's understood that anytime we don't tell you what number x, what set x came from, notice that we never said x is an integer here. It's understood that x then is always just a real number. We know what real numbers are? Raise your hand if you know what a complex number is.
I think I do.
You think you do? Well, shoot, then we might be in trouble. The real numbers are all the numbers you know that aren't complex.
Right.
Is pi a real number?
Yes.
Is the square root of 2 a real number?
No.
Yes.
Yes.
Is 1/2 a real number?
Yes.
Yes. If there's no imaginary part, it's a real number. If you're not taking square roots of negative numbers, it's a real number. Okay, so it's the numbers you were working with in your basic algebra classes. All your algebra classes, you were just working with the real numbers. That's it, over and over again. Integers are a subset of the real numbers. Every integer is a real number. Not every real number is an integer.
Yeah.
Maybe it's worth taking just a second to explain each of these sets really quick. Maybe we already did, I don't know. These are the naturals. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. These are the integers. So they have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and -1, -2, -3, -4, etc. Notice that every natural is an integer, but there are integers that aren't naturals. Alright, Q here is all the fractions.
Okay.
Anything that can be expressed as a fraction is in Q. Every integer can be expressed as a fraction. Give me an integer.
One.
Huh? 2? 2. There's it expressed as a fraction. -500. There's it expressed as a fraction. This is still -500, so it's irrational. So every integer is irrational. Not every rational is an integer. For example, 1/2. That's not an integer. not an integer. What are the reals? We won't worry about complex numbers in this class. What are the reals? Now they're pretty much any number you can think of. Pi, for example, is not a fraction. You can't express it as a number over a number. Square root of 2 is not a fraction. You can't express it as a number over a number. We'll prove that one later in the class. Okay? So that's a subset of that's a subset of that's a subset of that. Make sense? Alright, so when we don't bother saying where the number comes from, it's assumed it's a real number. So if we say x greater than 2, if x is greater than 2, then x squared is greater than x plus 1, it's assumed x is a real number. If we want to be a little bit pedantic, then we could say, let x be a real number such that x is greater than 2. You could have also just said, let x be greater than 2. That would have been fine. Alright. Now we're trying to show that x squared is greater than x plus 1. Right? Okay, 2. Then, since x is positive, we can multiply both sides of this by x, and it doesn't change the inequality. So then, since x is positive, we know that x squared is greater than 2x, multiplying both sides by x. Right? And 2x is equal to x plus x. Oops. Right?
Right.
Which is going to be greater than
X plus 1.
x plus 2, since x is greater than 2.
Okay.
Which is greater than x plus 1. Since 2 is bigger than 1.
Square.
Right? So we showed x squared is greater than x plus 1. So 3, therefore x squared is greater than x plus 1, and we're done. Right? Yeah. Okay, so there's a bunch of examples of direct proofs. Alright, now let's talk about a type of indirect proof. A proof by counterexample. If I said every integer, or if I said every prime is odd, what would you say? False. Why are you saying that's false? 2. You say 2 is not even, or 2 is not odd, I mean, sorry.
Right.
So you disproved the statement with one counterexample. So you just barely proved that not all primes are odd.
This is by way of contradiction.
Kind of. We're working up to by way of contradiction, and you could use by way of contradiction. You're just proving a statement's false. Right? So let's look at another one. Here's a statement that we need to prove is false. If a and b are integers, such that a divides b and b divides a, then a equals b. We need to prove that false. So proof. It is not the case that if a and b are integers such that a divides b and b divides a, then a is equal to b. And we're going to prove this by counterexample. What are two integers we could use? We need to find two integers a and b such that a divides b and b divides a, but a and b are not the same integer. And
2, 3, 1 and 2.
1 and 2. Does 1 divide 2?
Yes.
Does 2 divide 1? No. You need to find two integers such that they both divide each other, but they're not the same.
0 and 1.
0 and 1. Does 0 divide 1?
Um,
What's the problem?
Need to find two integers.
Oh, you can use a negative number.
There we go. 1. Observe that. What's the number?
1.
1.
1. Let's be more creative. Observe that 17 divides negative 17, and negative 17 divides 17, comma, but 17 is not equal to negative 17. And so we disproved it. We found two integers.
Nice.
Right?
Yeah.
Again, you had all the information you needed. You just had to think of it. Why not try a negative?
Start with the definition of integer.
Yeah, there you go. All right, so that's it for counterexample. That was a really small section. The last section today is on Boolean algebra. Boolean algebra. Sounds complex, but it's really easy. So first off, what is a Boolean? It's something that's true or false. The way that the integers were -3, -2, -1, 0, 1, 2, 3, blah, 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 blah. How many integers are there? Infinite. How many Booleans are there?
2.
2. It's like you're doing math, but you only have 2 numbers. Isn't that way easier than having to worry about infinitely many numbers?
Yeah.
So it's like these are your only 2 numbers in existence. Just true and false. Or sometimes we think about it as 1 and 0. And that's it. So that's what a Boolean is. True or false. We have operations on Booleans, the same way that we have operations on numbers. You can add numbers together, you can multiply numbers together, you can divide, you can subtract, you can raise them to powers, right? Lots of operations you can do on numbers. We have operations we can do on Booleans as well. We can do the not operation, we can not a Boolean. We can and 2 Booleans together, we can or 2 Booleans together. We can do the implication of 2 Booleans, or we can do the logical equivalence of 2 Booleans. Let's remind ourselves of each of these because it's the exact same thing we talked about in logic. So here's x, here's y, 2 Booleans. What are all the possible combinations of their values? You can have true and true, true and false, false and true, false and false. It's like we're building a table of the different operations. You know how when you were a little kid and you had like your multiplication table and it listed the numbers 1 through 10, 1 through 10?
Yeah.
And you could write out all the possible numbers. Now imagine doing that for every number in existence. Not stopping with 10. You can't do it, right? Because there's infinitely many numbers. With the Boolean, since there's only 2, we can do that. We can look at every possible combination.
Cool.
So you can't look at every possible combination of multiplying 2 numbers together. We can look at every possible combination of ANDing 2 Booleans together. So it's like the simplest algebra there is. So if we have 2 Booleans, x and y, all the possible combinations of their value are true and true, true and false, false and true, false and false. That's it. Right?
Yeah.
Now, if x is true and y is true, x and y is true. True and false is false. False and true is
False.
false and false is
False.
perfect. You don't remember doing logic?
I do.
Let's go back and make these logical statements. X is Donnie's holding a white marker. Y is Donnie's holding a blue marker. Set up the first scenario so both are true. Right? Now I say, is it true that I'm holding a black marker and I'm holding a blue marker? Yes, so true and true is true. Next scenario. I'm holding a black is true, I'm holding a blue is false. I say, I'm holding a black marker and I'm holding a blue marker. True or false?
Oh,
Okay, yeah. I knew this would come back to you. So, and then false and true is false, false and false is false. Alright, let's try the or ones. I'm holding a black marker or I'm holding a blue marker. True. Is it true that I'm holding a black or a blue marker? Yes. What if I'm just holding the black? I'm holding a black or blue marker.
True.
True. And if I'm just holding the blue, I'm holding a black or I'm holding a blue marker.
True.
And then if I'm not holding any markers, a statement is false. Wonderful. All right. Now the hard one. Implies. If I'm holding a black marker, then I'm holding a blue marker. True. Wait.
No, yeah,
Okay. If I'm holding a black marker, then I'm holding a blue marker.
False.
False. If I'm holding a black marker, then I'm holding a blue marker.
Vacuously true.
Here's how you think about it in your head. Is it false that if I'm holding a black, I'm holding a blue? Is that false? How can you say that's false? If I'm holding a black, then I'm holding a blue. Is that false?
No.
No. So it's
True.
true.
Yeah, it's so confusing.
This one is called vacuously true. If the antecedent is false, an implication is always true.
I liked how the book explained this with the politician as promised, because that made a lot more sense than purple dinosaurs and all that.
All right.
So it was pretty much saying that politician says that if he gets elected, he'll lower taxes. If he's not elected and the taxes aren't lowered, did he break his promise? Was he lying? And then if he wasn't elected, but he still managed to lower taxes by some outside sources or influences, did he break his promise?
You follow that? There you go. So yeah, read the book. The author puts a lot of thought into the way that he words things.
Wait, how can that be true?
False implies false is true. It's vacuously true. There's no cases to check. If I'm holding a black marker, then I'm holding a blue marker.
Okay.
There's no cases to check. It's vacuously true. We can't satisfy the antecedent. The if part, if the if part is false, then the whole thing's always true. Make sense? Okay. Next, logical equivalence. That just means x and y are the same Boolean. So top scenario, are x and y the same Boolean?
Yes.
Yeah.
Yes. Are x and y the same Boolean?
No.
No. Are x and y the same Boolean? No. Are x and y the same Boolean? Yes. Now we showed last time that x is logically equivalent to y, says the same thing as x implies y and y implies x.
Yeah.
And you can prove that with the truth table. We're not going to do that again today. We did it last time. Okay. Now we have our negator. Not x. If x is true, not x is
False.
false. What about here?
False.
What about here?
True. True.
All right, let's negate y.
True. False.
We're negating y. False.
True.
True.
False.
False. True. Okay. Now, going to show the distribution rule once. I showed you last time how to distribute a not over an and. I showed you not x and y is the same thing as not x or not y. If I tell you it's not the case that I'm holding a black marker and I'm holding a blue marker, if it's not the case I'm holding a black and blue marker, then either I'm not holding a black marker or I'm not holding a blue marker. Make sense? So let's try out the truth table and see if these are in fact identical. So we're negating x and y. We already wrote x and y here, so now we're just negating that. So the negation of x and y is false.
True.
Perfect. Now over here, we're ORing together these two negations. We're ORing not x or not y, right?
Yeah.
So we're ORing these two together. False or false is?
True.
False.
Wait, what?
I'm holding a blue marker or I'm holding a black marker. Don't try doing calculations in your head, don't say those are false, so I need to negate them and or them together. I don't know if you're trying to do that. We're just oring together these two columns. We're saying false or false is false. Why are you guys saying true?
False or false is false.
I'm holding a red marker, or I'm holding a black marker, or I'm holding a blue marker.
Yeah, that's true.
It's true that I'm holding a black or blue marker.
Oh, okay.
Okay. This will happen to you all the time. It's going to be obvious, and then you're going to get confused. And that's going to be obvious, and then you're going to get confused. That's the nature of logic. All right. So false or false is
False.
false. False or true is
True.
true. Right?
Yeah.
Or means at least one is true.
Uh-huh.
True or false is true or true is
True.
False.
true.
I was just measuring you, Donnie.
Oh, okay. Better have been. All right. Now one more that happens to be useful. We're going to look at this one. So this says not x or y. Right? Let's look at those really quick. So we're oring together not x and y. False or true is
False. True.
true to me.
True.
All right. Not x or y. False or false is
False.
false. True or true is true or false is okay. Now, does this column look identical to any other column?
Yeah.
Which one?
No. Yes.
Which one?
X implies Y.
The implication. Notice that those two have the exact same values. That means they are logically equivalent. That means they do, in fact, say the exact same thing. Now, so this is one other way that we sometimes think about an implication. So we know that an implication, when is an implication true? It's true when the antecedent is false, so it's vacuously true. That's these two cases. If the antecedent is false, then the implication is true. Or if the conclusion, the y part's true, then the implication is true. So if your conclusion is true or your antecedent is false, then the implication is true. So if your antecedent is false or your conclusion is true, the implication is true. So me saying, if I'm wearing shoes, then I'm wearing socks, is identical to me saying either I'm not wearing shoes or I'm wearing socks. If I'm wearing shoes, then I'm wearing socks. I'm not wearing shoes or I am wearing socks. Seeing the connection?
Yep.
So this is sometimes a useful way to think about an implication. Since remember, proofs are just a bunch of implications. Sometimes think about it this way helps. Still just an implication. Just worded in a much funnier way, in a way that might be easier for you to think about depending on the problem.
Okay.
Okay? Before we talk about properties, let's evaluate now some expressions. The same way that you know how to do 5 plus 2 squared, and it comes out to some number, let's evaluate some expressions here using Boolean algebra. So, false or false is false, or true is, then negate it is
False.
false. So you just evaluate that whole expression and came out to false.
Oh, this is awesome.
True and false is
False.
false. True or false is
True.
true. So over on this side of the implication, that all came out to true. True implies false is
False.
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 There we go. We just evaluated all that. That was a long way of writing false. Just like when you evaluate some massive expression that comes out to 25, that massive expression was just a long way of writing 25. Right? So that's why it's called Boolean algebra. You're doing algebra, but with Booleans. And you can evaluate Boolean expressions, you can solve Boolean problems.
I thought you said
This is
Boolean.
my favorite algebra.
Boolean.
Boolean.
Boolean algebra. And it's just using logic. And now you see the strong connection between Boolean algebra and logic. Okay, so properties of Boolean algebra. Probably should have actually gone over these before we did this, but you did right anyways. Alright, property 1. ANDing is commutative. X and Y is identical to Y and X. How would you prove that with the truth table? Write out X and Y, write out Y and X. They have all the same values in all the same places. Right? Right here we have X and Y. Right? If I would have written right here Y and X, I would have done true, false, false, false. So X and Y has the same value as Y and X.
Yeah.
So X and Y is identical to Y and X. So ANDing is commutative. Similarly, X or Y is the same thing as Y or X. So ORing is commutative. To draw some parallels, this is almost, Boolean algebra is almost, it's not identical to, but it's almost like thinking about all your T's as 1, all your falses as 0, all your ands as times, and all your ors as plus. It's almost like that.
Okay.
Very similar. So, the same way that multiplication is commutative, and is commutative. The same way that addition is commutative, or is commutative. Associativity, X and Y and Z is the same thing as X and Y and Z. We can add those two together first, then AND it with this. Or we can add those two together first and then AND it with this. And it gives you the same thing. Again, you'd prove that with the truth table. Similarly, X or Y or Z is the same thing as X or Y or Z. Doesn't matter which or you OR those together in, you'll always get the same thing. Now, truth is our ANDing identity. The same way that 1 is the multiplicative identity. X and true gives you X. Gives you back whatever X is. If X is true, this whole thing's true. If X is false, this whole thing's false. That's what we mean. And similarly, X or false equals X, the same way that X plus 0 equals X. False is your ORing identity. So if X is true, then true or false is true. If X is false, then false or false is false. So it just evaluates to wherever X is. Make sense? Okay, next. Distribution. Here's where it's a lot different from what we're used to. X and Y or Z is the same thing as X and Y or X and Z. That's how you distribute. You're used to this one for multiplication. When you had X times Y plus Z, it was X times Y plus X times Z. So similar there. Here's the weird one though. You can distribute an OR over an AND. So X or Y and Z is the same thing as X or Y and X or Z. So that one's a bit weird. So this is the one that we'll actually prove with the truth table here in a second, because I think that's the weirdest one. Next, X and not X is always false. The sky's blue and the sky's not blue. False. Similarly, X or not X is always true. What's the answer? 6 or not 6? Positive. Right? Okay. This one, we already showed one of them in the truth table here. We proved the other one last week. Not X or Y is the same thing as not X and not Y. If I'm not holding a black or blue marker, I'm not holding a black marker, and I'm not holding a blue marker. Similarly, not X and Y means not X or not Y, and that's when we did it there. Good?
Yep.
Alright, so those are your basic properties of Boolean algebra. We'll prove the distribution rule, since we already proved this one, and the other ones I think are pretty obvious. And then we'll be done for today. So come over to, make sure my table's showing. All right. So here's our table. Now, what am I showing? I'm showing x and y or z is the same thing as x and y or x and z, and then I'm going to show that this is the same as this. That's what we're proving. We're proving this with the truth table. Since these talk about 3 different booleans, here I have all the possible combinations that you could have for 3 different booleans.
Okay.
How many combinations are there? Don't count it, think.
9.
No.
8.
8. If I only had one boolean, x, how many possible values could x have? 2. Right? 2. If I added another boolean y, now there's 4 possible combinations. This has 2 possible combinations, and for each of its 2 combinations, we have 2 combinations for what that could be. So you're left with 4. If we add a third boolean here, z, now for each of the 4 combinations we have here, we have 2 options for what to give this. So now you have 8. And if I add some other boolean here, how many possible combinations would there be? 16. So adding one more boolean to your expression drastically blows up how many possible combinations are. Doubles it every time, right? So since we have 3 booleans here, we have 8 possible combinations. Now you'll notice if you just focus on this part of the table, that's the exact same as what we've been using right here. So this is all the possible combinations for y and z. This is all the possible combinations for y and z, again. And then this is pairing them all when x is true. This is pairing them all when x is false. Another way that you can see that. So you'll see symmetries to these tables. Make sense? Okay, so let's fill out the table now. And now we're just going to have to think about it all in our head because I'm not going to write out tons of columns. We're just going to do it all in one shot. We're going to evaluate this thing. So this is true or true is,
True.
and true is
True.
true. Let's go all the way across like this at a time rather than going down. So if everything's true, it's,
True.
and if everything's true, it's,
True.
and if everything's true, it's, oh, wonderful. All right. Now, true, true, and false. So true or false is,
True.
and true is,
True.
maybe it is easier to go like this. I don't know. Yeah, let's keep filling up this column. All right, so now we have true, false, true. So true, false, true. False or true is,
True.
and true is.
True.
All right, false or false is,
False.
and true is.
False.
All right. Now notice that for all these ones, x is going to be false. And false and anything is always false. You see that? So we can instantly know that all these are going to be false. Because it's going to be false and something, false and something, false and something. Who cares? Good? All right, let's fill up this one. Okay. True and true is.
True.
True and false is.
False.
True or false is.
True.
Okay. True and false is. We're looking at this one. True and false is
True.
false. True and false is false. Right? True and true is. True or false or true is. Wonderful. Now, true and false is. False and true is. Or true and false is. False or false is. False. Perfect. Now notice that for all these ones, x is going to be false, right? So false and anything is. False and anything is. False or false is. So all these ones are going to be false. So we show that these two are logically equivalent. They say the same thing. Now let's try and say it in words to see if we can make sense of it. I'm going to the store and, well, I don't know if I want these related. I don't know, maybe we can just do it with these three. So we'll make this one. I'm holding an eraser and I'm holding the blue marker or the black marker. What does that mean? That means I'm holding the eraser and I'm holding the blue marker, or I'm holding the eraser and I'm holding the black marker.
Okay.
You see it?
Yeah.
Okay. Next, let's fill out this one. So this one we've got, notice here we have, on these four we have x is true. And true or anything is always true. So true, 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 right?
Yep.
Okay. Now, over here, we have false or true and true is
True.
true. Okay, true and false is,
False.
or false is,
False.
false and true is,
False.
or false is,
False.
false and false is,
False.
or false is.
False.
Alright, next one. Okay, notice that for these four cases, x is always true. And so we have true or something and true or something.
It's
True or something is always,
true.
true or something is always,
True.
true and true is always,
True.
so true, true, true for those ones, right? Okay, next, looking at this case, x is false. False or true is,
True.
True.
false or true is,
True.
true and true is,
True.
alright? Now we have false or true is,
True.
false or false is,
False.
true and false is,
True.
False.
true and false is,
False.
false. Alright? False or false is,
False.
ended with anything is always,
False.
and if everything's false, it's
False.
wonderful. And notice now that this column is identical to this column. So they say the same thing. Let's read a statement to make sure it makes sense.
The other
Uh,
one is identical.
Yeah, we found
Right, we already showed that this was identical to this.
No.
That was the first case. Now we're showing this is identical to this. It's our distribution rule. We're proving it works. So I'll make our statement. I'm holding the eraser, or I'm holding a blue marker and I'm holding a black marker. Okay? I'm holding an eraser, or I'm holding a blue and black marker. Says the same thing as I'm holding an eraser or the blue marker, and I'm holding an eraser or the black marker. Make sense?
Yeah.
Good? Okay, so there we are. That's the end of the properties. Yeah, we'll end it there. I'll go get the printout of your homework and we'll go over homework from last week, but this is the end of lecture.